Okay, it's about time to get started one more time again. I think the things that what we have done on chapter one talk about the simple stresses and a way that what we combine all the things together, only one single stress and a way that's what induced in the workpiece or in the machine parts, things like that. In conclusion, a way that what you guys may figure out so many types of workpiece that experiencing external loading applied on the workpiece, things like that, and then experiencing the internal forces, things like that, for this many type of stresses induced in that anyway. So therefore, in chapter one, it's mean only one single stress only, just apply induced in the workpiece. So therefore, those kind of things we call simple stress anyway. And the things that what we keep in mind, we never ever allow the stress induced in the workpiece to be more than the sigma y or the corresponding tau sub y that what the workpiece gonna have it anyway. So therefore, we have a safety factor to be able to withstand with that anyway for those kind of things for the design, things like that. Okay, and chapter two, we're gonna talk about the pressure vessel, things like that. You guys have studied about it before in solid mechanics, things like that. So therefore, you guys may review it by yourself. I also just have written down the textbook, things like that. You may review by yourself. Anyway, I like to skip it. You may read it out and review it by yourself, things like that. Okay, and then let's go for chapter three. I'm gonna talk more in details, things like that. Let's review all things together, things like that. In chapter 3, the headline is going to be on the combined stresses and failure theories. Anyway, so it means we're going to have two stories individually. Anyway, one is combined stresses. It means in this chapter we're going to have more than one stresses induced at the same time, things like that. Or it might be like this: it's going to have more than one external forces applied to the workpiece, things like that. Okay, or even one single forces, things like that. External forces may induce more than one stresses, things like that. So therefore, we're gonna call it combined stresses, things like that, induced in the workpiece. Only at the same time, things like that. Okay, and then at the same time, we're gonna have this the failure to help us. Okay, to never allow the tiles of white or six sigmas of white, things like that, to be more than the things that what happened there inside the member, okay, inside the workpiece, things like that. You may figure out, see, just we just have been taught already in chapter one, but they've never ever allowed the stress induced in the workpiece to be more than sigma y or either tau sub y, things like that. So therefore, this kind of thing, we're gonna have another help for the failure theory to make decisions, things like that. Okay, for the work peaks to be able to do on it anyway. Okay, so leave it out for you guys, things like that. Okay, so the things that what we're gonna approach on it is gonna be the things that what I have mentioned about it anyway. It's gonna basically loading that apply to the machine's components or member may be classified into three. One, normal loading causing normal stress. Two, bending loading causing bending stress. And three, torsional loading causing shearing stress, respectively. However, in most cases of mechanical engineering design, more than one type of loading may apply to the machine's component or members simultaneously. This is the thing that what I mentioned just a while ago anyway. Accordingly, the load that apply to the member more than one type can be classified as the combined loading. Okay, let me you give an example for the combined loading for the things that what apply in the figure 3.1 anyway. So you may figure out this is some kind of like a eccentric loading anyway. See, the real figure is got the figure on the right hand side anyway. We have the eccentric loading acting right there. The P force acting there is not right there at the center of the cross-sectional area right there. See, the P force is acting there, okay, essentially with an E distance apart from the center there, okay. So therefore, the P force there, I just applied, okay, the moment couple, things like that. What you guys study on the statics course, things like that. See, I just move the force of P just be right there at the center. So therefore, when I move the force of P right there at the center, I'm gonna have the associate moment. Okay, right there, moment is gonna be equal to P times E automatically. Is that right? So therefore, I'm gonna have, see, the moment couple, okay, induced right there due to that I moved the force of P up there to be right there at the center there. Because as I see, when P just move it right there at the center, I'm gonna have automatically, see, due to the force applied right there at the center, I can apply sigma equal to P over A. Distribute, see, just perpendicular, distribute uniformly over the cross-sectional area, things like that, equal to P over A. Okay, it's going tensile force. So I just apply the sigma A respectively. Okay, and then this one is gonna be bending all the way, right? So it means at the top part is gonna be pulling force, and then the down under is gonna be compressive all the way. So, or I might say in the top parts is gonna be some kind like a tensile stress. Is equal to sigma equal to m times c. All right, right? It's bending all the way, and then down under is gonna sigma c is gonna be minus, right? Because it's compressive m times c over I respectively. Okay, so therefore these two kind of things we gonna add it up, okay, by vector, right? So sigma a add up the sigma t is gonna automatically is equal to the sigma total there, p over a plus sigma c over I, and then down under here is gonna be some subtraction anyway for the vector. There is gonna be sigma c is equal to P over A minus sigma M times C over I, things like that. And so therefore you may figure out there we have a neutral axis there, ends up in dot A and A, things like that is the neutral axis. Remember, neutral axis is gonna be the axis that gonna be have the stress equal to zero anyway. See, even if you go there, neutral axis is the axis that have the stress equal to zero. It's not necessary to be right there at the axis of symmetry anyway. See, this is the axis of symmetry, so it's going to be there. It's going to be a way of distance of A anyway. See, this is the things that what we gonna have it here anyway. See, so just for this kind of things, see, that what we just concerned with this kind of thing anyway, see. So if we just consider about the damage happen here, the damage happen here, if we increase the p force here more and more here, is most likely the damage most likely to be happening right there at the maximum stress there, right? The maximum stress gonna be down under at appear to be at the surface, the top part there, most likely to be damaged there. So therefore, we automatically gonna make the decision, okay? Have a look at it, or just make a judgments that the most likely failure is gonna be at the top parts there, okay? So therefore, we just check up the most likely failure is gonna be at the top part there. Okay, if the sigma total there is gonna be less than the sigma y, so the material being used up there is less than the is going to be greater than the sigma total there, it's going to be okay. Okay, if it's greater there, it's going to damage you. Okay, so that's why the safety P can be made. It will be calculate there for that. Okay, this is the things that what's going to be a good explanation of the combined stress anyway. Okay, and then the stress components anyway. See, this is a very good example here. So the good example is gonna be this is gonna be some kind of like a cube, okay, of the explanation of the static equilibriums of the stress interdimensional of the static equilibrium anyway. For instance, like this is the box, okay, of the stressed, okay, under static equilibrium anyway. For instance, see, I apply an external force all over to the bodies of some kind of solid member, things like that. Okay, and then I just pick some of the box inside there out anyway. So it's most likely we have a box in the Cartesian coordinate system of x-axis, y-axis, and z-axis, respectively. Look like that. I'm gonna have a sigma perpendicular to the box there, okay, and sigma y there, and sigma z is there, and then I have another tau xy. You may figure out that tau xy is gonna be have a perpendicular to the x-axis and a direction to the y-axis there. Okay, and then tau yz perpendicular to the y-axis there. Okay, yz. Okay, perpendicular to the y-axis and have a direction towards the z direction there. Okay, again tau xc perpendicular to the x-axis there. Okay, and then just moving towards the z direction there. And then since it's in equilibrium anyway, tau xy equal to tau yx, and yz equal to zy, and then we have xc equal to zx respectively. So in conclusion anyway, we always have a sigma x, sigma y, sigma z. We have 3 sigma, and then we have another 6 tau. So we have 9 of stresses in equilibrium anyway. See, so therefore this is a kind of automatically. See, in general cases we have three-dimensional stress element. We have a sigma of 3, and we have another 6 shear stresses anyway. See, so therefore if okay we just move the z-axis to be very thin. Okay, everything the z-axis just make it thin. Okay, so therefore the z-axis is going to be very thin because the c we just take the z-axis out, things like that. If we have any z direction there out, things like that, everything's going to be collapsed out to be a plate, look like that. We have any z direction, we just have a thin plate to be like that. Okay, so therefore everything's gonna move out to be a sigma of x and sigma of y. We have two of them of sigma, and then we have another two stresses, shear stresses anyway. Okay, so therefore it's going to look like that automatically. See, so therefore we have 2 sigma x, sigma y, and then tau xy and tau yx is going to be equal to each other. Okay, so therefore again, okay, now we would like to transform of sigma x and sigma y to another plane. Okay, for instance, see this kind of thing. See, in figure A, see, this is going to have an x-axis and y-axis. So if I just move it over to a theta, okay, the theta angle have make some inclination to an theta angle of the y-axis, for instance. See, theta of theta angle to the y-axis, things like that. See, so this is the theta angle. So therefore, we have a plane of this kind of plane. Okay, we have a triangle. We have a plane of that. This kind of plane. See, we have a plane that what we have a perpendicular to the plane of this is we call it sigma n. Okay, another one is we have a tau sub and things like that. Okay, this kind of axis we have a sigma n. The sigma n we just make some kind like equilibrium. Everything is under equilibrium, okay? Static equilibrium, of course. So therefore we just make everything in a sigma n direction. We make a projection of sigma x in the sigma n direction, and then sigma y in the sigma n direction, things like that, and then the outside xy in the sigma n direction, xy and sigma in direction. We're gonna have equation of 3.1, okay, in equilibrium. This is the relationship of figure B there, okay. This is the relationship there. So therefore, we have a sigma n equation there, okay. So it's we generate an inclination to an angle of theta there. This is a sigma n. a new plane. Okay, and then tau sub n is gonna be a shear stress parallel to the plane of theta there. Okay, therefore 3.1 and 3.2 is gonna be another plane that what we feel interesting about those kind of plane anyway. So therefore in generation, okay, we transform in any plane, we can use equation 3.1 and 3.2 as our weapon to generate in any kind of plane anyway. See, we can move it whatever we want to. Okay, therefore we want to have it maximum, right? We would like to know where is the maximum that we want to. If we know where's the maximum, we just trying to figure out where is the point of maximum, and then we never allow the maximum to be much more than the sigma y or tau sub y is tau max is not more than the tau sub y. That's gonna be fine, right? So therefore I'm gonna check it out for equation 3.1 and 3.2. Where is the tau max and sigma max? Where is it anyway? So the maximum, so therefore 3.1 I make a differentiation. I make a differentiation of 3.1 respect to zeta. So therefore, I set equal to 0. I find the angle of tangent to zeta equal to this equation 3.2. This is the direction. So therefore, I know this is the maximum, right? So I plug it, right? 3.3, the result of that, I got two of them. So therefore, I plug it back, okay? I plug the value back into 3.1 there, okay? So I find, okay, the represent the value of 3.1 we call the principal stresses. Principal stresses mean the maximum stresses anyway, see? So maximum sigma anyway, so therefore this one is going to be sigma 1 and sigma 2 anyway. This is the principal stress anyway. See? So therefore 3.4 and 3.3 is going to be direction and the value, the maximum value, respectively. This is a principal stress, max sigma anyway. See, highlighted place. And then we do the same manner with the equation 3.2, okay, respect to zeta. So we got equation 3.5. This is going to be the maximum direction of the tau max anyway. So again, we just plug it back into equation 3.2. We find the maximum shear, okay, shear stress in a way. That what we have an equation 3.6, we call it maximum shear stress in a way. So therefore, okay, we just can be explained equation 3.6 and 3.4 in terms of Mohr circle. Anyway, you guys quite familiar about Mohr circles already, right? Mr. Mohr induced this kind of thing for the explanation anyway. See, we plot out the circle here, we call it Mohr circle anyway, with an axis of sigma there and tau up there. Say, you may pick up the blue color here representing the axis of the um, principal stress. Anyway, we have a sigma 1 and sigma 2 respectively. See, and the red line there, it's gonna be Cartesian coordinate systems. Anyway, we have a sigma tau xy, sigma y, and tau minus tau xy respectively. And then we have a green line there. We're gonna have a maximum shear stress. See, you got it there, right? Remember to zeta there, the angle in here in Mohr circle is going to be double for the real thing. If we got the angle of the real figure is zeta, the angle in the Mohr circle is going to be double there. Okay? So therefore, this is the Mohr circle. Based on the Mohr circle, we got another addition there. We're going to have a tau max there equal to sigma max minus sigma min over 2, right? See, this is the radius, right? Radius of the circle there. Okay? So this is the thing that what you guys recognize about it already. Okay? So this is the thing. So please highlight it, okay, as an equation that when we're going to use it. Okay? 3.6 is going to be tau max and direction of 3.5. And then principal stress is going to be 3.4 and 3.2 respectively. Okay, so therefore, okay, okay, let's go for another one for things that what we're gonna go for. See, practically, okay, most of the cases for the machine design, okay, for the real world, things like that, that what we're gonna go for. Typically, all the model, okay, all the stresses gonna be only one axis of sigma, and tau gotta be look like this only. It's never ever have an axis of y at all, only one direction. So everything gonna be very simple then. And axis of y, we gonna take everything's out. We throw it away. So everything's gonna have an axis of x all the way. So everything gonna drop out. So all the equation there is gonna drop out to be equation 3.8 and 3.9 respectively. Highlight it please. So now from now on, all of you guys gonna use equation 3.8 and 3.9 all the way. All the way. Okay. So therefore, since now, okay, I still use equation 3.8 and 3.9 forever. Forever. See? This is the things that what I still uses up to now. This is gonna be the things, my weapon to make a design course, things like that. Okay? So this is the things that what we're gonna use it anyway. So this is the principal stress theory, 3.8 and 3.9 is gonna be the things that we're gonna use for the tau max anyway. Okay, shearing stress, maximum shearing stress. So let's have a quick look at the example of 3.1. Determination of maximum force of P. There is the bracket as shown in the figure. P force is acting up there. So bracket is going to be the thing that what we just put something on it. This is going to be just a J term, look like that, okay? And we typically put some kind of like a weight, a huge weight on it. And this kind of thing have a cross section or like a T term like that, okay? So this is gonna be the things that gonna be some kind like make some kind like a fancy decoration, things like that. Have a cross section like a T term, look like that, okay? So this kind of bracket is made of cast iron. This is gonna be cast all the way, okay? So therefore, of course, the cast iron have a tensile up is gonna be up to 30 megapascal, okay? But the compressive is up to 70s anyway. Okay, so you may figure out the free force P there, okay? So therefore, it's gonna be damaged. The maximum gonna be around the point of A and B respectively. So therefore, let's see there. I gonna move the force P there, gonna be right there, okay, at the centroid, okay, centroid at the of the P there, okay, P gonna be at the centroid of the T cross section there. So I move the force of P gonna be up there, okay. I'm gonna have an associate of the moment there, okay. So therefore, see, I'm gonna have the P force there, gonna be pulling force there. So therefore, P over the cross-sectional area is gonna be the tensile all the way, and then the moment there is gonna be the bending moment is gonna be the tensile on A and the compressive on B, things like that. Okay, so therefore, let me have a look at it. The moment there is going to P times D is going to be equal to that. The tensile side, okay, is going to be uh, A side, okay, P over A plus the moment times Y over I, things like that. Okay, I just plug in everything's there. On this side B, compressive, okay, I just plug it in the compressive side. So that's why I got the P term respectively. So therefore, I just got the answer for the lower value as the answer. Okay, example 3.2 is going to be curved beam, things like that. Okay, for instance, like the P term there, I'm gonna move the P force to be right there, and then I got the force P, and then I'm gonna have the moment associated anyway. Okay, so to have a look at it. Okay, another thing. Okay, the failure theory. Okay, let me read it out for you anyway. So this is the thing. It's gonna be the things that what you're gonna use is a lot anyway for the failure theories anyway. The failure theory is going to be look like that. For the safety and durable reason in the mechanical energy design, the allowable stress induced in the machine's component should be kept. I'm sorry, to be less than the strength of its corresponding material. This is the thing that what we use in. I mean, just talking so many times is mean the sigma induced in the workpiece or the tau induced in the workpiece should be less than the corresponding tau sub y or the sigma y respectively. In the case of combined stresses, the strength of the corresponding material used for the calculation may not be equal to that obtained for the mechanical property obtained from the strengths, the tensile strengths. The strength of the material used for the calculation of the machine's component design under the combined stress can be determined by using the failure theory. You see, because that's why we have the certain failure theory to help us anyway. The M&A failure theory, however, the maximum normal stress theory, number one. Second, maximum shear stress theory, number two. Third, the octahedral shear stress theory are the most common used failure theory. We have three of them, very popular. Let's go one by one then. Number one, maximum normal stress theory. Okay, normal stress is mean. Okay, this theory failure dependent on the numerical magnitude of the principal stress. See, seems like they just concentration on the sigma max only. Okay, so therefore this theory is widely used for the brittle and high shearing stress materials such as cast iron. Highlight please. So therefore this is good for the cast iron only. So therefore, if you would like to have an formulation, so therefore we can apply on it that the sigma 1 equal to plus minus is going to be the positive and negative. It's going to be tensile and compressive respectively. Sigma y over n in the case of absolute value of sigma 1 greater than sigma 2 respectively. And then sigma 2 is the plus and minus in the same manner. So equation 3.11 respectively. Okay. So therefore, if we use equation 3.10 and 11, plot out for the boundary of safety, things like that, the late line there is going to be the boundary of safety. Anyway, inside, the safety factor is more than 1. Out of the boundaries, the safety factor is less than 1. On the line, safety factor is equal to 1 anyway. So therefore, please let the stress gonna be inside there. Okay, so safety factor should be more than 1 anyway. Okay, so the second theory is going to be maximum shear stress theory. It's said again. Okay, in here, this theory states that the failure depends only on the magnitude, the maximum shear stress attained in an element. This theory is widely used with the ductile material and sometimes called the Tesca criterion. Okay, so this one is good for ductile material or steel, things like that. So therefore, based on this, okay, this one, okay, if we apply the maximum shear stress theory, so therefore sigma 1 minus sigma 2 over 2 equal to tau max, things like that, equal to plus minus sigma y over 2n, and it's a safety factor. So therefore, based on the tensile test, tau max equal to sigma tau sub y over n, things like that. So therefore, we applied on it. We gonna have equation 3.13, where tau sub y equal to sigma y over 2. Highlight please. This one very careful. Okay, you better highlight this one. Okay, for the maximum shear stress theory. Okay, tau sub y equal to sigma y over 2. If you compare to chapter 1. Chapter 1, you talk about the simple stress. Okay, the tau sub y estimate to be 0.6 sigma y NOI. See, that only one single stress NOI. Okay, but this one we have a combined stress. The tau sub y equal to sigma y over 2. Be careful here. Okay, so therefore, sorry, if you plot out your graph, okay, by using equation 3.12. Again, the late line there is going to be the region of safety. Inside the safety factor is just more than 1. On the line is safety factor equal to 1. Out of the border, the safety factor is less than 1, respectively. Okay. Another one is going to be maximum octahedral shear stress theory. Okay. This theory states that, okay, the failure depends on the maximum of the octahedral shear stress attained in an element. Okay, this theory got the same result as obtained from the maximum distortion energy theory. Sorry. Credit for this theory is often given to Mr. M.T. Huber from Poland, Mr. R. Wormses, okay, from German, and it transferred to be the uh, United States of America. Accordingly, this theory is also sometimes called the warmest stress theory or Huber-Henke criterion. Okay, so many names anyway. So you may heard me about the warmest stress anyway a lot anyway for the stress analysis anyway. Just before you guys talk about it, octahedral. Okay, I would like you guys to just understand about the octahedral plane first. What does it mean by the octahedral stresses anyway? See, octahedral is mean like this, okay? We're gonna have a sigma 1, sigma 2, and sigma 3 respectively. What does it mean here? Sigma 1, sigma 2, and sigma 3 here is gonna be the maximum, the principal stress axis anyway. See, at the principal stress axis, we just have a stress only. Okay, this is going to be the principal stress. It's never ever have a shear stress at all. Okay, at this axis, see, we're free of shear stress. Okay, so therefore, at this axis, at the, is that cube anyway, we just make the same direction cosine as the plane of, blue plane here. Okay, I cut the same direction cosine. Okay, this plane A, B, C, we cut the same plane here, just make some inclination and equal direction cosine to the plane of sigma 1, sigma 2, and sigma 3 respectively, same inclination angle. Okay, and this is the plane of octahedral. And then the things that the stress that um that's parallel to the plane of ABC, that what we call octahedral planes. Anyway, this is the things that what we call octahedral plane. So this is going to be some kind of like a 3D dimensions anyway. So therefore, this is going to be good for the things that what we're going to design for 3Ds anyway. See that what we now they use a lot with the computer design, things like that, with the principle of the one Mrs. Stress anyway, that what we call a lot nowadays with the computer design, things like that, with the stress analysis, things like that, with the finite element analysis, a lot. Anyway, sometimes we call octahedral stress, things like that. One is stress the same, anyway. See? So therefore, see, when I just make the under the equilibrium anyway equation, tau octahedral there, I just make a projections of sigma 1 and sigma 2 and sigma 3, and then I make a projection of the tau OC there, the tau OC octahedral plane. I got the relationship of equation 3.14, and then, based on the tensile test, the principal stress sigma 2 and sigma 3 is equal to 0. So therefore, and then sigma 1 equal to the sigma y for the tensile test, things like that. So I got the sigma 2 equal to 0 and sigma 1 equal to sigma y, things like that. So the equation 3.14 drop out to be 3.15. So therefore, I plug it back there at equation 14. I got equation 16 there. So equation 16 there on the right hand side is look like collapsed out. Sigma 3 is 0 for the plane there. So that's why equation 17 there is turned out to be an ellipse term. Okay, so equation 17, okay, I plot it on the graph there on equation 10. I'm sorry, figure 3.10 there. It's going to be the late line there. So I plot together, okay, superimposed together with the principal stress theory, and then the maximum shear stress theory and maximum principal stress theory are together. It means, see, the region there is going to be in the same axis there. So it means the smallest region show us here, okay? The regions of the maximum shear stress theory is going to be the smallest region there. So it means the second theory there show us to be the safetiest anyway. See, because it's smallest show us there. See? So in conclusion, the maximum shear stress theory, okay, show to be the most safety anyway, okay? Because that's why you see the small dot there, okay, show the smallest region there, okay? So therefore, this is the thing that what I mentioned, see, that's got to be the most safest anyway. So therefore, I make a declaration on the equation there, makes the thing simpler on equation 13, 17 there. And then I just make a tau sub y equal to sigma y over square root 3. So equation 3.18 is going to be the things that we're going to use for the equation of the maximum octahedral shear stress theory anyway. Okay, which is tau sub y is going to be equal to 0.577 sigma y respectively. Okay, highlight it please. So this is the things that what we have those are kind of four three theory together. Okay, and then let's go for an example that what we gonna go for it. Let's have a quick look at the example here. Example 3.3, a solid shaft subject to an axial loading of 10.5 and bending loading of 2040 newton meter and torsional loading of 225 newton meter is made of 1020 HR steel and the safety factor 3.5. Okay, given the shaft diameter by using the failure theory of maximum normal stress theory, the maximum shearing stress theory, and octahedral shear stress respectively. So you may figure out, okay, it's a 3D, okay, figure, and then this is a 2D one, okay. We have three external loading, axial loading, torque, and bending moment, respectively. First thing first, the material is 1020 HR steel. I got sigma y of 210, okay, and then axial loading, I got sigma A F over A, see, is gonna be, uh, I got the D square as the unknown there, and the bending, okay, M times C over I, okay, and then the tau, shearing state to the torsional loading, okay, so therefore I'm gonna add up the sigma to sigma there, okay, add up together. So that's why I use the normal stress theory, sigma 1 and sigma 2 by equation 3.8 there, okay, I just add it up together, okay, for the sigma term, and the tau is there, so I just from equation 3.10 sigma y over n, okay, I just plug it there, n is given by the problem set, so by trial and error, okay, so I just got the answer of 73.59, okay, 4, things like that. And then for the shear stress theory, I got tau sub y, be careful, huh? 0.5 sigma y, I just plug everything there by trial and errors again. I got a D equal to 73.635. Okay, 6653. Okay, I'm sorry. And then tau sub y for octahedral is 0.577 there. I plug everything there. I got the answer there. So based on the result of the three theory, I got the maximum shear stress theory as the largest diameters anyway. See, that's the things that what we prove that this is the safety things that what we have got from the answer anyway. See, And then example 3.4, you may try it by yourself. And then 3.5, I used to put this one as the former exam, maybe like 5 years ago. I know where you may have a look at it. See, I have a force acting on it, and I move the force of F to be right there at point A, okay? And then I have an associate moment, okay, right there. So therefore, I got the sigma, I have a tau, I have a tau due to the V over A, and then I have a tau, okay, to the torque there. So that's why I have a total tau there, okay, and then I just plug everything that back there. I got the answer there, okay. Let's see the problem that's set there. So okay, number one, okay, try it. Number two, number three, four, five. Okay, you may try it. Number six. Okay. Number seven. Okay. Number eight. Okay. Number nine. So you may try. Submit to me number 10, please. Okay, you do it and submit to me. Number 10, huh? Okay. Number 10. Okay, only one single problem, okay? Number 10, huh? Everybody solve it and then submit to me as an assignment, okay? So this is gonna be it for the lecture for chapter 3, okay? So I stop my lecture for chapter 3 for today anyway. Thank you.